Hey there humans, Mr. D here. In this video we're going to be carrying on our discussion of quadratic equations and quadratic functions and how we can gather information about these quadratics, namely vertex, axis of symmetry, y-intercept, min and max, domain and range, from the function itself, whether it's written in standard form or more specifically today we're going to be focusing a lot on vertex form. And we're going to be doing all of this without actually graphing the function. So no graphing calculator will be needed today. You don't need anything with graphing capabilities. You might need like a simple scientific calculator, but nothing too crazy. So let's get some basic foundational stuff out of the way first, and then we'll really put it to work. So as we discussed in a previous video, we have standard form of equations for quadratics, which is ax squared plus bx plus c. And that's really good for telling us the y-intercept of a quadratic. And then we have vertex form. And that's a times the quantity x minus h squared plus k. And that gives us the h and k values, which will then tell us the vertex of the equation of the quadratic. Hey, I already goofed. So the vertex would be h comma k. And as I discussed in a previous video, make sure you're being careful with these h values because it's always going to be the opposite of what you would think. So if it's a minus here, it'll be a positive there. All right. So you'll notice there's a common theme between the two. They both feature that a value. So that the a value is going to be whatever the coefficient or the plain old number attached to your squared term. So your a value is going to be one of two things. If it's positive, you're going to have a graph that opens upward. And if it's negative, less than 0 just means negative, it's going to be opening down. And we kind of know that from our parent function discussion about whether or not these graphs got flipped or not. The vertex is always going to be the highest or lowest point on the graph. So that's going to depend all upon on whether you have an upward opening parabola, in which case your vertex would be the minimum, the lowest point, or do you have a downward opening parabola, in which case your vertex would be the maximum, the highest point. So depending on our orientation of the graph, we're either going to have a low point or a high point. And then we have the axis of symmetry, and that's going to be a vertical line that passes through the vertex. And apparently, I forgot to write the word vertex over here. Yay for me. So the axis of symmetry is always going to pass straight through the vertex. It will be written as an equation of x equals some plain old number. And that number is always going to be the h value from your vertex. So whatever that h value is right here, that's going to be the axis of symmetry. All right, so here we have two separate examples of what a parabola might look like. If our a value is positive, we have an upward opening parabola. You'll notice the vertex is on the axis of symmetry. Since it opens upward, our vertex is going to be at the lowest point. Same thing over here, we have a downward opening parabola, so my a value, the coefficient of the x squared, has to be negative. Since it opens downward, our vertex is going to be the maximum, the highest point. Now, when it comes to domain and range, your domain for these quadratics is always going to be all real numbers, negative to positive infinity. And the reason for that is I have an arrow that's kind of pointing left and an arrow that's pointing right, and there's really no spots of discontinuity in between. So our graph never stops. So eventually this function is going to hit every single x value. So every x value is going to be defined. There's nothing off limits. So my domain for these is going to be negative to positive infinity, and that's going to be true every single time. For every quadratic, your domain will be negative to positive infinity. So that should be a free point whenever you see that in a quiz, test, homework, whatever. Your range, however, well, your range is going to depend on the vertex. Okay, so your range is always going to steal the y value of your vertex And it's either going to be that y value up to positive infinity or from negative infinity up until said y value. So it's either going to be negative infinity to whatever, so whatever that y value was, or it's going to be that y value up to positive infinity. And that all depends on whether or not we have a downward opening parabola or an upward opening parabola. Because remember, if it opens down, our vertex is going to be the highest point. So it goes downward forever, and then it obtains or attains a maximum. And then if it opens upward, we have our lowest point at the vertex, and then it goes up forever and ever and ever. All right. So now let's focus on equations in vertex form. We've already discussed all of this. It's just written out formally, so if you need to pause to write this stuff down, not a bad idea. When we have a function written in vertex form, we're going to pay attention to these values of h and k, and that's going to tell us the coordinates of the vertex. Again, be careful with the h value because it's going to be the opposite of what you would intuitively think. Your axis of symmetry, you're just going to be plagiarizing the h value from your vertex, and it has to be written as x equals that number. Let's get into some examples. So here we have a few examples. We want to first determine if they open up or down, and that can be determined from our a value. So just going through all of these examples, I'm going to highlight the a value. Finding the vertex. Well, these are all written in vertex form, so I can just kind of steal the h and k values. The y-intercept might take a little bit of extra thinking. And then the axis of symmetry, well, that goes hand in hand with our vertex. But the axis of symmetry, we really only care about the h value, or the x value of the vertex. All right, let me circle back to the axis, or the y-intercept real quick. Normally in standard form, we could figure out the y-intercept super easily. Unfortunately, these aren't in standard form, so it's not going to be as easy. But really all we have to do is just plug in 0 for x, and then whatever you get as the y value, that's going to be your y-intercept. All right, so not too terrible. All right, so for this first graph, since my a value is positive, I know it opens upward. I've got a vertex of positive 4, 1, which then means my axis of symmetry is just 4, because remember I'm plagiarizing the x value from my vertex. And then the y-intercept is 0, 49. Now we got that 0, 49. If I plugged in 0 for x, this is what my function would look like. Zero minus 4, that's negative 4. Negative 4 quantity squared, negative 4 times negative 4, that's a positive 16. So this is 3 times 16 plus 1. Well, 3 times 16 is 48. Add 1. Shabuya, we got 49. That's going to be the same for all of these, right? Number 2. I've got a negative a value. Why did I choose that color? Negative a value, so it's going to be opening downward. My vertex is negative 1, 3. Axis of symmetry, I just plagiarized my own work. And again, for y-intercept, just plug in 0 for x, 0 plus 1, square it. You have a negative out front, add the 3. So 1 squared is 1, negative, so negative 1 plus 3 is 2. And same thing for our last function. We have a positive a value. We're given the vertex. I can steal the axis of symmetry from the vertex. And by plugging in 0 for x, I can figure out the y-intercept. 0 plus 5 is 5. Square that, I get 25. Half of 25 is 12.5 minus 2. Boom, 10.5. All right. Well, now let's take a look. What would the axis of symmetry be based on these functions here? So I'm not given a graph, I'm not given an equation, but I'm asked to figure out the axis of symmetry, and that's going to be x equals something for each one of these functions. Well, you notice some of these values are matching, right? So if I'm looking at the y values, I have a bunch of negative numbers. They're slowly getting closer to zero, closer to zero. Boom, now it's positive, and then it cycles back down to negatives. So if this table were to go down even further, it would be a safe assumption that I would see negative 15 and then negative 35 as my following values. Therefore, smack dab in the middle of it all is my axis of symmetry. And since it's x equals, we're taking the x value, so this first one would be x equals 4. On the next example, I'm seeing matching 2s, I'm seeing matching 10s. It's not shown, but it would be a safe presumption that 26 would be at 0. So my axis of symmetry then has to be between these two folks. Well, what's between 2 and 3? Well, that would be 2.5. So x equals 2.5. All right. Now let's talk about mins and maxes. With minimums and maximum, minimums, maximums, all you're doing is stealing the y coordinate from the vertex, okay? And it's up to you to determine, is it a min or is it a max? So if I look at these two examples, this first one, our vertex is going to be 2, negative 3. And the second one, our vertex is negative 4, 8. For both of these, I really only care about that y value. Let's see, number 1, it's positive out front, so it's opening up. So that's a minimum there. Number 2 is negative, so it's going to open down, which means we have a maximum. So all we have to really do is just kind of formalize our thoughts. So we want to find the minimum or maximum of this quadratic. For number 1, we have a minimum of negative 3 when x is 2. That's all we have to do. I was lazy and wrote min. You guys can write the word minimum if you want. Number 2, we have a maximum value of 8. When does that happen? That happens when our x value is negative 4. That's all we have to do. So not a whole lot of thinking involved, just kind of formalizing the thoughts. All right, so these two examples that we're going to do, it's going to be the exact same idea as the previous ones. However, we're throwing in a few new items. Is it a min or a max? And then domain and range. Well, we automatically know domain for all of these, right? It's going to be negative to positive infinity. And then range, that's going to determine or be determined by our vertex. So if I look at number 1, it's positive, so it's going to be opening upward. So my range here is going to be something, infinity, because it goes up forever. Oops, that should be a bracket. And if I look at my second one, it opens downward. So it's going to be negative infinity, some number. All right. So let's take a look. Vertex. We already discussed how to do that. Axis of symmetry, you're just plagiarizing a value from the vertex. Y-intercept, we plugged in 0 for x and see what our function value was. The minimum is just rephrasing what our vertex was. So my vertex is negative 1, negative 5. We're just rephrasing that to write out our minimum. Domain is always going to be negative to positive infinity for these every single time. And our range is just going to steal the y value of the vertex And that's it. Number 2 is going to be the exact same thing. We know how to find the vertex. Axis of symmetry is built into the vertex. The y-intercept, plug in 0 for x, and see what our function value is. The maximum value is just rewording the vertex using words. I guess only one word, at. Domain is always going to be negative, positive, infinity, and then our range has to involve our maximum value, which is the y value from our vertex. Since this opens down, because it was negative, our vertex is going to be the maximum value, so that's the highest point of the range. All right, onward we go. Now what we want to do is write the equation of a quadratic in vertex form. I have vertex form written up here in case you guys forgot to write it down earlier. You'll notice now they're giving us the vertex of an equation and then one single point. What they're not telling me is if this opens up or down. I could probably use some logic to figure it out, but they're definitely not telling me an a value. So with all of these values, your vertex is going to tell you the h and k for your function. So we have our h and k value here is going to be 1 and 2. And then the point is going to have your x value, and then the y coordinate, well, that's just f of x. So what we're going to do is we're going to plug in these features into our equation and then kind of see what happens when we solve backwards for a. All right, so let's get going. For the first one, I'm going to have -5 equals some mysterious a value times x, which was 2, minus h, which was 1, squared, plus my k value, which was 2. So now I just need to solve this out. -5 equals, let's see, 2 minus 1 is 1, square that is 1, so that just becomes a. So a plus 2, subtract 2 to the other side, I get a equals -7. So my function is going to be f of x equals, we just figured out that a value, -7. -7 times x minus h, so x minus 1, quantity squared, plus k, which was 2. And that would be our final answer. Not too shabs, right? Not too shabs. Let's do one more. We'll do number 2, and then we can go ahead and skip number 3. Number 3 will be available on the PDF. So if you want to see the work for that, feel free. All right. Number 2 is going to behave the exact same way. We're given a point, so that's an x and an f of x value. -2 equals some mystery a value times 1 minus -3, so 1 plus 3, squared, plus 6. So again, I'm just stealing the values that were given and throwing them into the equation. All right, let's go through and solve. -2 equals, let's see, 1 plus 3 is 4, square that, I get 16, so 16a plus 6. If I subtract that over, I get -8 equals 16a. Divide both sides by 16. See those cancel over here. -8 over 16. Hey, that reduces. -1/2. So I've just found my a value, which means I can write out the function. F of x is -1/2 times x plus 3 squared plus 6. All right, last one. Applications, aka word problems. Whenever you see applications, that just means word problems or visual problems based off of a graph. Here we have the jump of a dolphin. Write the quadratic equation that models the dolphin's jump. Hopefully you guys are looking at this graph and screaming internally, at the sheer fact that our axes aren't labeled. What are these textbook publishers trying to prove here, man? What's going on with that? I can only assume that the y-axis is like the height above sea level, and the x-axis is maybe the horizontal distance, or maybe time. I don't know. I would love to know, but I don't know. But we want to figure out what is the function here. So I need to know two things. I need to know the vertex, and then I just need to know some random points. All right, so let me zoom in here. The vertex, it looks like it's at 3, 7, but it might be at 3.5, 7. I'm going to zoom in and see if that helps clarifying things at all. It looks like it would be like right about there. Just for simplicity's sake, we're going to assume it's 3, 7. So 3, 7 will be our vertex. And then we need some other points on this graph. So we want to find some place where it cleanly crosses at one of these little grid squares. It's like one of these little grid corners. Here looks pretty good. Maybe 12, 0. I'm thinking 0, 6 might be a good option. Typically, if you can use 0, something or something, 0, that's going to be in your best bet, because zeros are typically easy to deal with in equations, because anything plus 0 is just itself. Anything times 0 is just 0. So let's use that y-intercept, which was 0, 6. And now we're going to do exactly what we were just doing before. And we're going to plug in our values to the basic standard form of a function. I know my h and k value, and I have an x and an f of x. So 0 will go in for x, 6 will go in for f of x. I'm going to have 6 equals some mysterious a value times 0 minus 3, quantity squared, plus 7. We do some math here. 6 equals, let's see, 0 minus 3 is negative 3. Square that. Anything squared is a positive number. Negative 3 is 9. So 9a. Ooh, I have to be careful. My a's look like 9s. So 9a plus 7. Subtract the 7 to the other side. I'll get negative 1 equals 9a. So then a is negative 1/9. So my function will be f of x equals negative 1/9. Sorry for the penmanship. Times x minus 3 squared plus 7. And just visually looking at that, I know my a value should have been negative, right? Because I have a downward opening parabola. So negative 1/9, I'd say that makes sense. All right, that's it for this video. If you have any questions, please let me know. Don't be shy with questions. And as always, folks, good luck, have fun, be safe, roll tide.